Welcome back to Gadget Engineering, and in today's video we're actually going to be comparing two versions of the PSBSAP 20 hammer drill. To the left we have the A1 version. Here we have a production date 08/2020, and the B1 version we have here, which is a 2021 June version. So exterior wise, we have some basic changes, a little bit of a color scheme change on the chuck clutch selector. Otherwise, they look very similar. We have a little bit of a different finish on the Gearcase housing, but all in all, they look very similar. So here we have the A1, and to the right, the B2. So as you can see, no real big changes. We still have the all-metal Röhm chuck. Stout construction. The specifications have also stayed the same. So we have our 80 Newton meter brushless motor on both. So let's actually have a look if anything's changed, because one of the potential issues these tools have had that they've shared with their non-hammer drill, the smaller version, the PASBSAP 20, which has a 60 Newton meter rating, is that the spindle lock that allows you to undo these chucks has sometimes failed to lock. And obviously there's some kind of locking dogs, or as we'll see, locking pins that enable this spindle locking action, and these seem to fail, especially in the 60 Newton meter version. So let's have a look inside if anything has actually changed between these two versions, and we'll see that once we open them up. So I've taken the liberty of pulling most of the screws out to ease our entry into the drills. As you can see, they are very much wobbly. So for disassembly, you just have to remove all the visible self-tapping screws on this side, another 4 screws holding the Gearcase, and then there is this bezel that is just clipped onto the back. There's 2 clips either side that you have to just pry off with a screwdriver, and then the whole case should just pop off. So we can start with the A1 version. We can just pry the Gearcase a little bit forward and remove our housing piece, revealing the insides of the tool, and we do the same on the B1 that we have here. So here are the ratings on both of those. You can compare, very, very similar indeed. So once inside, we can see that the basic setup is very much identical. We have our battery input here, our LED. They both have this small magnet hidden inside the case that is to retain a bit that you can store on the back here. They both have similar or almost identical looking trigger modules that we'll have a look in a moment. But just to ease our analysis, we're going to split the Gearcase. So for that, you just hold on to the brushless motor, remove the Gearcase, and the same on here. So just pull that off. So as we can see on both, they share pretty much an identical design as far as the electronics go. So we have our battery inputs. We can see they've changed their wire supply in the meantime. So within this year, the question is really, is it the same factory that's manufacturing both of these, and the B1 is just the newest production run to replace stock for this year? Or is it an upgraded design, maybe bid out to a new manufacturer? We'll see that they share so much in common that it's obviously been manufactured at the same place in the same factory, probably on the same tools, on the same dies, we'll see. So as far as the battery connector, here we have these sort of semi-siliconed wires, fairly soft, just soldered onto this connector piece. On the B1 version, we have these much stouter. These are solid copper wires. These are stranded, so not much flexibility here, not that it really matters. Here we see that these have been partially molded into this battery connector piece. So they've obviously soldered the wires to these metal pins and then somehow molded it into the connector. So you can see, if we remove this pesky LED, that these wires have been thoroughly molded into this piece. So when we get into the trigger module, so I just remove this down LED, 5mm jobby, nothing too surprising. As you can see here, we just have the LED lens, the Gearcase switch, the direction switch, and this is the control for the 2-speed Gearcase. So as far as the electronics go, we can see that there has actually been a fairly substantial change in sort of design philosophy. On the B1 version, we have just thin gauge wires going to the trigger control, so all the switching is being done in the circuit board that's mounted to the brushless motor. So here I think we have 6 wires that are going to be sending information about the directionality, the speed setting, nothing really more to be done switching wise inside this module. On the A1 version though, we do have some big gauge, same gauge 14 as the battery input wires that are actually going into the trigger module. So we have, I believe, 5 wires that are smaller gauge, that are just signal wires, again for the direction control and the speed selection. But there is obviously some kind of switching going on here with these thick gauge wires that go into this into the capacitor board. So the battery positive and negative go into this board, and on the B1 version they just pass through this capacitor and go into the brushless motor drive PCB without going to the trigger here. The positive loops into the trigger module and is switched inside and loops back out here to connect to the brushless motor. I'm not sure what kind of design and control is going on here. I don't see any really big heat sinks on the more basic trigger modules. You'll see sort of a metal plate on the side where there's a transistor or a MOSFET bonded to it for thermal control. This is not the case, although obviously these wires are here for a reason that aren't present in the newer version for some kind of switching. Of course, switching the positive supply on a brushless motor doesn't really make that much sense, but it seems to have a reason. Curiously enough, both modules are actually identical manufacturer-wise. I don't know if you can see those model numbers, but both of them are from the same manufacturer. So this is Qianhe FA2-16/1WEK. The A1 version is 36 volt DC, rated at 15 amps, I believe, and the newer version is rated 42 volts DC, 0.2 amps. So obviously the A1 version is doing some sort of switching inside the trigger module. A nice observation is that we have this Buna and rubber boot that should protect from any dust ingress. This is present on both versions. So this is definitely a very decent design as far as the trigger modules go. So continuing further on up, we have our 2 brushless motors that seem to be identical. As far as the major hardware, we can see that the heat sinks are obviously quite different. So on the A1 version, we have this fully potted PCB module that is enclosed in this heatsink. And on the B1 version, we have an exposed PCB on the side with the heatsink just screwed on up front. If we compare the gauge of that aluminum casing, we can see that actually the B1 version does use a thicker gauge aluminum compared to the A1 version if the sidewall thickness is the same as the front, which actually might not be the case if you look at the screw holes. That seems to be a little bit thicker than the sidewall. So as far as heat sinking goes, the A1 version kind of looks more stout with the potted circuit board to mitigate for any vibration, but maybe some airflow between this sort of heatsink plate might allow better thermals on the new version. So that's pretty much a wash as far as those capability goes. The motors themselves have a fairly invisible marking. Now you might be able to see it here. So they are marked BL4820 20 volt Parkside Speedmaster, and as you can maybe make out on this board, it is the same marking. So obviously within that 1 year production cycle, their nylon reserves have gone from transparent to black, but the overall build is pretty much identical. We have these two small ball bearings on the back. Both are the same module, 625 PS, I believe, or 635, made by different companies. Obviously, they're restocking as time goes on. We can see that the electrical sort of input is different in both, although it doesn't really make much sense why they had to change this. So on the newer version, we have our input capacitor just sticking straight out. Here we have it on this little 90-degree daughter board facing the front. So we'll see actually this design consideration of the capacitor location has actually had an effect on the molds they used for both drills. So this is the A1 version, this is the B2, and you can see that the molds are pretty much identical except for the position of this screw tower that has moved to the left or moved to the right on the rightmost on the newest B1 mold. And why has that changed? Well, it's just simply to accommodate for this new capacitor location that in the B1 version, or the A1 version, it's off to the right. In the B1, it's sticking back. So they had to move this self-tapping screw tower out of the way. So obviously, the factory manufacturing the tool didn't have much input on the design of the ancillary components of the brushless motor. So they had to quickly reshuffle to make the molds fit. And interestingly enough, since this is the newer version of the mold, you can try and sort of follow up this design change if they really have been using the same mold. So on this side, there's not that much evidence of that, but if we look into the other half of the molds, you can actually see that they are in fact using the same mold. So A1, B1 here, or B2, been saying it wrong all the time. So you can see these slight imperfections on the mold that sort of indicate some manual filing or adjustment to the mold. So on this edge here, you might be able to make out this sort of little bit of beveling on this mold. And if we look at that same area on the newer mold, we can see it has that sort of beveled edge here too. So we can really say that this is the identical mold that they've been using. You have to look for some kind of manual imperfections. Here we have the extraction pins, so they have some filing marks when they've cleaned that up, so you can't really go by that. But you can look at any sort of imperfections in the mold. And if we look towards the area where the previous screw tower was, so it would be in this position on the newer mold, you can actually see that there is a footprint visible, the circular area here, where they've moved the tower over here on the mold they were using. So this is sort of interesting to follow up their sort of design revisions through the series. So most of these parts are PA6 nylon glass fiber reinforced 30%, fairly stout. They have the TPE overmolding, which is very comfortable and gives it a nice surface texture. So if we go on further, so we've gone through the cases, all very much identical except for some of the screw terminals. We can come back to the electric motors. So here we just have our rotors that we can pull out with a little bit of force. So these are permanent magnet rotors with our brushless motors that are 6-pole, 3-phase, I guess. We can do the same on the A1 version. So again, pretty much identical. We can see they've had their plastic granules change color in the meantime. Nothing too exciting here. But if we take a closer look at the PCBs and the heat sinking, we can sort of get a picture of what's going on there. So if we actually take a look inside one of these brushless motors, I guess this might be swamping out, but you might be able to make out the three SOT23 components on the bottom there. Those will be the Hall effect detectors that will be detecting the position of the rotor as it's turning. So on both of these, the newer version is much easier to remove since it's not potted. If we pull, of course, these 3 screws, which I've removed 2 previously, we can expose parts of the PCB. So we can see this heatsink here. When we remove it, we have our thermal paste spread onto the transistor packages, or the MOSFETs more likely. So we have 2, 4, 6, 8, 10, 12 MOSFETs here. So it being 3-phase, we're having 4 MOSFETs controlling each phase. We have this larger MCU chip here that's doing all the control. This is some kind of voltage converter. We actually have a pinout on the side here for actually programming. So we have clock and data pins here that were used at the factory to program this whole device. So interesting layout here, been nicely conformally coated with this heatsink with the thermal paste. I think this should be delivering a very good thermal performance. So on the A1 version, of course, we have everything potted. So we've pulled this one screw. So we're not going to be able to see the PCB, but we can sort of bend it back and sort of have just a quick cursory look. Nothing much to see here. But what surprised me is that we have this terminal pulled out and we have this hole in the PCB. Darn. So we have 3 phases. So we have 1 main phase going to the board, the second wire going to the board in here, and this is actually supposed to be connected here. So this literally just pulled out when I took the screws and shimmied this board off. So we actually have one of the phase studs that have come out of the board just due to a cold solder joint here. So poor soldering, definitely on the A1 version. You can see how this is sort of a cinched position. I guess they could have soldered it without the stator installed, so they would have had more access. But if any of you have problems with your A1 versions dying with the motor being stuck or dead, or maybe it will vibrate or something, open it up and check that all 3 of these stator winding to PCB studs and connections are actually well soldered, because this one just came off on me, and this will still be possible just to solder through this little opening here, but definitely be aware of this potential issue. So as far as the brushless motor goes, that's pretty much all there is to say. We can pop those off to the side, and let's take a look at the gear cases, which are the most interesting component of the hammer drill. So here we have the A1 version, the B2, change of color scheme and sort of design. Both still have the Röhm Extra 50 model spindle locking clutches. And here we have our gear cases. So this is a two-speed gear case. We have the control with this wire loop here that goes to the movable lever on top, and as we disassemble these, you'll see that it's set up as a planetary, as is pretty common on these tools. So this one already comes pre-disassembled by yours truly, but once we get in here, we can actually have a look at how it's all set up. So this will be full of grease, and you'll definitely want to be careful disassembling this, or you'll have just gears laying all over the floor and you won't know how they go together again. So if you remove it like this, you'll actually remove the whole gear train as one piece with its parts pretty much intact. So at the front we have our chuck mechanism, our clutch that determines the basically Newton meters you'll be sending off the chuck. So if you set this low, you'll have the clutch slip once you reach a certain force or pressure. Then we have our drilling setting, which basically locks this slipping clutch not to be able to move. And then we have our hammer function. So as far as these slipping clutch settings go, it's actually a spring that's mounted somewhere in here, and it is controlling these pins or little studs that you can see coming out, and it just increases the spring tension on the studs. So when you go from 0 to 21 here, you're just increasing the resistance on the studs. So I have it set to 1 now. I can still compress it fairly easily with the screwdriver. If I ratchet it up to 21, it becomes pretty much impossible to move, so I can't compress that anymore. When you switch it to drill, I think you just increase the spring tension just so much more that it becomes so hard that it most likely won't slip. But when you change it to hammer drill, you're not actually modulating any effect of the spring, you're just unlocking an additional function where the chuck now has a bit more flexibility to move in, and then when you rotate it, you can hear that sound. It is bumping up on some wedges, and it's producing that oscillating motion that is pushing the chuck in and out to produce that hammer drilling function. So if you turn it back to the drill mode, you can see the clutch doesn't have that degree of movement anymore, and you don't have that oscillating action. When you turn it back, the clutch can move in, and then it's bouncing up on these wedges that are making the hammer action. So here we have the drive shaft. Of course, now the spindle lock has been removed. This is actually hidden inside this element here, so we're going to be losing a bunch of parts putting this back together, but pretty much you just have these ball bearings here that are all aligned into these holes that, as you'll see in a moment, we have this ring gear that goes over top of them. So this is the slipping clutch. This is not the hammer drilling system. This is the slipping clutch. So you have these ball bearings that are standing on those spring adjusted studs underneath. So once we drop this toothed ring gear on them, depending on the spring tension of the studs pushing on the ball bearings, if spring tension is high, the ball bearings will, since this is fixed in place, it can't sort of slide up and jump over those ball bearings with its toothed surface. It will actually just, if we can get these ball bearings back in place, it's always quite nerve-wracking dealing with these gear trains since there's so many small parts to fall out. So once it's set in place, if the spring force is high on those ball bearings, depending on the direction of rotation, this ring gear will hit and stay and keep turning the drive shaft. If the spring force is low on those studs, as it turns, it will be able to depress those ball bearings and spin in place. So once we move on, so the next sort of layer of the onion is our spindle lock mechanism. So if we remove this thrust plate or thrust washer, this actually goes on top of this drive. You can see here there's also a small spring that is placed onto the chuck drive shaft. So this ring gear or this little washer just fits onto there like that on top of that spring. And then we have our next element of the puzzle, which is the spindle lock. So yeah, we're going to need that if I want to open up that chuck. So the way this works is that you have these little pins which serve as the spindle lock dogs. So to assemble this, it's probably easier just to remove all of these pins, and then we can move to the spindle lock. So you'll see many parts just lying around, but it won't be that difficult to actually reassemble them. So the next most important component is this locking collar, locking dog that has this sort of intricate design of teeth and open spaces that allow some rotation. So you'll see it's indexed on the shaft. I don't think it really matters which way it goes on. So you can slip this onto here, and then comes the careful alignment of these little pins. So they go on to somewhere in here, so you have to align them with these small indents here. They don't go into the large square holes, they go into the 6 half-rounded spots on this locking collar. So you'll just have to carefully place them in here, which certainly takes a lot of patience. So bear with me in just a second and we'll have that all set up. So as you can see now, we have all those little pins aligned adequately. This will provide the locking action. So I won't turn it now because they'll all lose their indexing. But if you try and turn it counterclockwise, this pin will slip out to here, and between this extending tooth edge and this wall that it's in will lock and jam the shaft from turning. If it's going the clockwise direction, this pin will stay in its position, but this one will roll towards this canting outside edge and again jam the chuck output. So mating to this piece, we have this element here with the 3 teeth sticking out. So this has to go in with the teeth positioned into the open spaces. So the teeth can't collide with the pins, they have to go into the open spaces. So as you can see here, we have this sort of wallered out profile of the chuck drive shaft, so it can go in 180 degrees either way. So if we align it this way, we can see that there is a tooth that is impacting the pin, so all teeth would be impacting the pin, so we have to turn it 180 degrees to have the teeth going into the open area. So let's position this. And if it's aligned correctly, you'll be able to push it down against the spring force, if you remember this spring beneath, and you'll know it's locked in correctly. If one of the pins have sort of fallen out, it will not align, and it will just go in crooked. So the pins themselves are 3.4 or 3.39 millimeters nominal width, and I believe it's about 5.8 millimeters in length. The length doesn't really matter, but that 3.4 or 3.38 width is something that can wear and cause failure of the spindle locking mechanism. So I'm not going to take this apart again, but in the 60 nanometer Newton meter non-hammer drill version, they only have 4 of those pins providing the spindle lock mechanism. So you can see now when I'm turning the chuck, I'm locking this thing up and it's not able to spin, and I can let's see which way. Okay, yeah. So now I can actually open up the chuck so it won't spin. But if on the input side I turn the this planetary gear, you can see that I can turn the chuck, even though from the output side I can't turn it. It locks. When I turn it on the input, it moves freely. So that is providing the spindle lock function on this Röhm chuck. As I said, the 60 Newton meter version has only 4 of those pins, so anywhere either in the pins or on that central locking collar or of the walls of the gear case itself, since all of the other pieces except for the pins, they are hardened steel, but all of this is just sintered steel, which is prone to some wear. As those tolerances wear further, you're going to get slippage in the chuck, and certainly 6 contact points are better than 4. So I don't think we're going to have this kind of spindle lock failure in the hammer drill version. We'll check if there have been any improvements on that front on the B2 version. But that's pretty much how that works. If we look into here, which is the Planetary gear set, we have basically 3 stages. This is the final output stage that mates with this spindle lock here. This is set up as a gear ratio, so 1 to 3.3 on the first Planetary. I believe it's 15, oh no, it's 5 on the second Planetary stage gear reduction, and again 3.3 on this final output. And the way you change speed, so when you go from the first to the second gear, which is 2000 RPM and 400 RPM, you actually engage or disengage the second stage Planetary gear case. So if we pull this top plate off, so this final Planetary that is, okay, falling apart on me here, but it is basically just set up in this output stage. So we have the Planetary on the output. This is the sun gear, these are the planets, and this is the ring gear. So this is 3.3 to 1, so every 3.3 turns of this shaft will provide 1 turn on here. So you can see if I fit this, and of course it's missing plenty of its gears, but as this turns, the chuck also turns slowly, and you can also see the clutch action. If this ring gear is free from the ball bearings that are retaining it on the bottom, it is able to jump over and not provide any output. So if I'm holding this ring gear to stop it from moving, we can see the chuck moves. If the ring gear is free to move, you might be able to see that. See, it's wanting to spin on itself, and anytime it is spinning on itself, it's not giving power to the chuck. So that's how the slipping clutch works that you can set there. So in here, we have our two-stage Planetary. This is the second stage that is controlled or enabled and disabled by this wire that you can see is still set up on here. So just flicking this wire switch, what that does, it actually raises and lowers this outer ring gear that we have here. So on these sort of little tabs, you can see from both sides it moves up. So when it's in the up position, you can see it here. It's pretty much locked against rotation, being indexed in these grooves. So it's not able to turn when it hits this wall. So in the up position, when the outer ring gear is locked, it is not able to turn. The second stage Planetary, which is a 5-to-1 gear reduction, is enabled, and it is reducing the input speed. When you go into the fast gear, the 2000 RPM setting, you pull this ring gear down outside of these metal grooves that stop it from turning, and it is actually able to spin and is basically put out of action. So you can see here I have our brushless motor input, and as I turn this, the outer ring gear is spinning. It is not performing any gear reduction, and as you can see, once I got this, the drive gear, the sun gear on here has another outer set of gears that actually interface with that outer gear, lock into it, allow it to spin. So basically this whole second Planetary stage is taken out of action when you switch to the fast gear. So the way it's set up, we have our sort of first Planetary that uses the brushless motor input as its sun. These are the 4 planets, and the ring gear is the bottom gear you can see in here. So there's 2 gears. The top one is the movable one for the second gear. The internal bottom one is the one for the first gear Planetary, and it is fixed in its position, while the top one can either spin when in the low position or locked in the top. So the gear reduction total for first gear, or the slow gear, is 55-to-1, and the second gear is 11-to-1. So the brushless motor is actually turning at some 22,000 RPM, and that's brought down through either 2 or 3 Planetary gear cases down to either 400 or 2,000 RPM. So let's just brush these random parts to the side. After a bit of time on the healing bench, they should come back into action. But let's check if we've had any changes or improvements on this design with the new version. So for that, we have to pull out the wire engagement for the gear case. So you're going to have to pull it out of the holes, and then you have these metal studs on the side that are just sitting loosely in the plastic that you can just, whoops, I launched that across the room. Hopefully I'll be able to find that. So you can just push these off to the side and again release this, and this baling wire basically comes off. Make sure not to lose those pins. And then you have access to the 4 machine screws on the perimeter here to release this gear case. Another interesting fact, as far as materials go. So both the A1 version and the B2, if we do the sort of scratch test, you can hear that. So this is nylon with glass fiber reinforcement. And curiously enough, they've actually indicated this. There's a little bit of a stamping. I'm not sure if you can see that on this stud here. They've actually, where is it? Okay, it's on this side here. On this stud, you can see that there actually is a marking there, but they've pretty much covered it up with this positioning stud. So that's a bit of a fail in design. So let's get this open. So let's just undo these 4 screws. So again, we have spilled our guts here. Interior design wise for the chuck and the metal gear case housing looks pretty much identical. Looking at the other parts, so here we have these studs that are participating in the slip clutch. So I think there should be 6 of those. There we go, all 6 of those. Then we have the spring that goes onto the drive. Then we have this ring with 6 ball bearings. Then we have this slip clutch with the built-in ring gear. That's the same. Then we have our retention. So then we have our locking collar here. And let me just see. Okay, yeah, here we go. So I was missing the spindle lock mechanism, as you can see. So dogs look pretty much identical. The locking mechanism, and you can see here it's been retained nicely inside this gear, is pretty much exactly the same. So you have 6 pins, you have this internal locking collar, and between these edges and the walls, which is both sintered metal, we have these pins that are hardened. So I don't think the pins themselves would wear. I think these walls or this locking collar, these exposed points will wear to the point when turning this gear. You can see, so it's pretty much locked up now. The only way it would turn is if you used this piece. Let's see if I can demonstrate that here. If I aligned it on the outside, and you can see now it's very much willing to turn, since the teeth on this dog is pushing pretty much if you're going counterclockwise. So it's pushing this pin to stay in its groove, while this pin, just by the rotation, is forced into place, and vice versa. So let's just get a quick reading on the measurements of these pins, just so I'm not called a liar. So pretty much we have, these are very slippery, but that should be fine for a radius. So 3.37, probably, yeah, 3.38, probably nominal 3.4 millimeters. And lengthwise, so yeah, 3.76, 5.76, 5.8. That should all work fine. So we've gutted these 2 drills. Pretty much identical mechanical design inside. So I guess we can take a quick peek at the Planetary here. I don't expect we'll be seeing anything drastic going on. So Planetary wise, nothing changed. The speeds are again first gear 400, second gear 2000. So none of the Planetary geometry will have changed. So as far as the 2 drills go, the A1 and the B2 version, pretty much identical, made in the same factory apparently, as we've seen on the markings on the mold. A slight change to the brushless motors and the wiring thereof. Original version had the silicon wires. The new version has the solid core. Both seem to be 14 American wire gauge. The most major change to me is the change in the trigger module, that the new version doesn't have any switching action going on, which to me is better. Best to have all the switching going on the PCB, where there is much better heat sinking and cooling with the motor fan. This version here has the potted PCB with the, maybe you could call it a superior heatsink, but that potting also has an effect on thermals. So temperature-wise, the new version I think would even be better off. Only problem on the first one, this is very much anecdotal, but we have our cold solder joint breaking the connection on one of the phases. So you can really see it's very much a failure of the solder joint, and not so much anything very much structural, because you can pretty much just reseat that joint, resolder it, and it's done. So it's just not had enough heat to bond that solder onto the pin, which is obviously a low thermal resistance part where it's dissipating the heat very quickly, so a bit tricky to solder. So all in all, both drills seem to be pretty much the same quality, pretty much identical design, except for some minor revisions to the brushless controls, slight change to the switches. Otherwise, gear train and all the drive components are identical. No material changes there, just some optical little updates on the color schemes. Chucks are exactly the same model and build from Röhm. So pretty much whatever version you get, A1 or B2, you're just as well off. No improvements to speed. The brushless motors are identical again. So fair to say that these are just a second production run to fill little shelves and not an upgraded, revised technical improvement. So thanks for watching this video. I have quite the job here putting these tools back together in working fashion if I don't want them to stay permanently resident on the healing bench. So I hope you enjoyed this video and that you'll be back for further teardowns and technical analyses. So do like and subscribe if you enjoyed this, and see you next time. Bye-bye.